the worst case release scenario requirements. They really focus on low likelihood, high impact potential events. The other part of the equation, or what they'd like to see are, as part of these regulatory programs, are alternative release scenarios. Things that are more likely to occur, but still would have off-site impacts. The idea being these are things that might occur conceivably during the life of the facility that can have an off-site impact. You want to analyze those. You want to understand those and feed those into the other part, one of those three main issues that are required as part of the regulatory requirements, which is the emergency response program. So that's how all that links together: the off-site consequence analysis, the prevention program, and the emergency response program. All that pivots around understanding what can occur and what the impacts are. So let's look at some of the specific requirements. What you're trying to do is really look at off-site population impacts. As you recall, process safety management is a requirement that was promulgated by OSHA, and it focuses on safety of plant workers. EPA's risk management programs and the state accidental release prevention programs focus on protection of the community based on EPA's jurisdiction and the other states' jurisdictions of protecting the community. So the key element is determining these off-site population impacts. You identify a circle of concern, or how far out that impact can get, and then you estimate the population within that area. It can include residents, it can include institutions, parks and recreation areas, and major commercial office and industrial buildings. And use of the most recent census data allows the population to be estimated. And you're not supposed to analyze it to the individual. You don't have to drive around and look for daycare centers in your area. This is meant to give the regulator and you a perspective on what those impacts might be. And of course, the census data, the software that provides it, allows you to estimate to 2 significant digits. That's a requirement. So as part of the determination of these off-site environmental impacts, you want to also identify environmental receptors. And you can use information that's provided on local USGS maps or in any other data source that provides you with the kind of information in terms of environmental impacts. So you're looking at off-site population, off-site environmental impacts as part of the overall jurisdiction and responsibilities that the EPA and the state programs have. Now, how does that impact with hazop studies? Again, all these come together. They're not meant to be individual and distinct and disjointed programs. The hazop study facilitator, as they're doing these things, needs to understand consequence analysis. It helps you identify important hazop study scenarios. If you're taking a team of 20 people, running through it, and as a facilitator, spending a lot of time and resources analyzing something that has just an operational blip on the process and may result in a few $1,000s loss, that's not something you want to spend all these resources on. So understanding basic OCA concepts is super important. Bless you. The hazop study can also validate the kind of off-site consequence analysis scenarios that you choose, especially for the alternative release scenarios. Looking at things and having the team validate and say, oh, this could credibly occur during the life of the facility, we need to make sure that's properly analyzed, can help you to pick out and prioritize the 1, 2, or 3 scenarios that you might want to analyze as part of your OCA for the alternative release scenarios. And also as a facilitator, although I've heard some facilitators go by the, gee, I'm a facilitator, the team needs to understand what's going on. I don't agree with that. The hazop study facilitator needs to have a good technical basis to guide the team, to know when the team is going in the wrong direction, and understanding the chemical process, general process issues, and also off-site consequence analysis phenomenology really helps the facilitator do their job properly. When you're facilitating, you really need to be thinking about how does this scenario propagate, or does the team properly understand the ultimate consequences so that they're risk ranking it properly. So let's talk about general OCA modeling parameters. When you're looking at toxics, you're looking at basic endpoints, or concentrations, levels of concern. We talked about that earlier. Toxic chemicals like ammonia, hydrogen sulfide, they have a certain amount of milligrams per liter, parts per million, different ways of representing concentrations that can cause potential health impacts. The toxic thresholds that are chosen by the EPA are usually ones that don't cause an immediate fatality. Usually they're things that if somebody is in an area that they get exposed to it for an hour, there's a certain impact. In most cases, it's an impact associated with with impeding their ability to respond or evacuate. So that's what's picking and driving these concentrations of concern. For flammables, explosions can yield overpressure events. An overpressure of 1 psi is a limit that's often chosen to have an impact, and we'll talk about that in a couple minutes. The radiant heat, thermal radiation effects, a radiant heat level of 5 kilowatts per square meter for 40 seconds is a typical threshold that you might have some impact, and you need to prevent those kind of impacts. Lower flammability limits, getting above a concentration where if it finds an ignition source that can cause a significant overpressure event, is often a level of concern that you pick so that you don't build up concentrations that can light off and cause either a deflagration or detonation. Other issues and key parameters are wind speed and atmospheric stability class. For a worst case scenario, a lower wind speed and more stable environment is chosen that allows concentrations to be maintained for long distances downwind. For alternative release scenarios, less conservative, more realistic assumptions are chosen, a different stability class, and a higher wind speed that is more representative of what you typically would see during a release. Again, to get a realistic potential impact so you can feed that into your emergency response planning. Ambient temperatures and humidities are also key things, key parameters that go into this OCA modeling. For the worst case scenario, regulatory requirements are highest daily maximum temperatures for the previous 3 years. If you don't have those, then they basically default to 25 degrees centigrade and 50% humidity. For an alternative release scenario, you're allowed to pick a typical temperature and humidity data from some observations that may be made from a local met station, and you feed those again to identify what are you likely to see during an emergency. Surface roughness, a term you may not have been exposed to before. Urban environment has lots of obstacles, things that cause a disruption in the flow of toxic gases, and what that does is it kind of mixes things up a little bit, allows it to disperse a little bit easier, so it doesn't build up the level of or concentration of toxic materials as far downstream. Rural environments that don't have buildings, that may have flatter land for longer periods, allow higher concentrations to be maintained for longer distances downwind, and those rural environments can yield further distances to that endpoint or level of concern for your toxic chemical release. When you're looking at these release considerations, the regulations have you split things up between passive and active mitigation features. Passive mitigation features such as dikes, enclosures, berms, drains, and sumps, those are allowable. That's physically there. You can take credit for those kind of features when you're looking at worst case scenarios. Worst case scenarios, they do not want you to take credit for anything active. Anything active such as sprinkler systems, deluge systems, water curtains, neutralizing the material, excess flow valves, flares, scrubbers, emergency shutdown systems that have to actively do something are not something that the EPA or the state accidental release prevention programs want to have infused into looking at that release, because they don't want to have to count on these systems or think about how likely they are to work. They want to use the worst case scenario to characterize the potential hazard that that facility poses to the community and to the environment. So let's talk a little bit more about flammables. Flammables have, as we talked about before, have a level of concern where you might, if you find an ignition source, it might light off, ignite and form a detonation or deflagration, and you have over high pressure and thermal limits that you want to be concerned about to prevent the injury of personnel and to have other propagating impacts. Characteristics of these flammables that you want to consider are things that cause overpressure, thermal radiation impacts, and for falling into these programs, there's usually a quantity that the EPA or the state accidental release prevention programs set so that if you're under that quantity, they consider it a relatively minor impact to the community, so you don't need to be covered as part of their program. When you're looking at the different chemical properties, a lot of things like molecular weight, boiling point, dispersion characteristics, vapor pressures, enthalpy of combustion, and lower explosive limits all come into play to help you identify the hazard. On your screen, you're looking at some example properties for hydrogen, methane, propane, and butane. And what it does is it gives some insights in terms of how understanding those chemical properties can help you understand the hazard and make sensible decisions on where to focus in terms of off-site consequence analysis. If you look at the methane, propane, and butanes, as you look at molecular weight increases, you see that they're roughly proportional to the enthalpy of combustion, or how much energy comes out in terms of kilojoules per mole. What that means is certain weights of material as they're released. When you're looking at it on a weight basis, you're getting similar amounts of energy that come out of that. And understanding the boiling point can give you an idea of if you have a release of this material, is it going to be a buoyant gas? Is it going to be a heavy gas? Will it stay a liquid? If it comes out as a liquid under pressure, is it going to rapidly volatilize and boil? All these things come into play in terms of how you model the impact and what software you pick for it too. And of course, upper explosive limits and lower explosive limits give you an idea of where you might have concerns if it finds ignition sources. Some example overpressure consequences. I'm not going to go through this, but this is just a handy reference table. Hopefully you can read it on your printouts of different pressure levels and what the impacts might be. And you can see why 1 psi is chosen as a generally applicable level of concern. Okay, so let's talk about release issues and what's actually going on. Basically, it's important to keep in mind that when you're dealing with flammables, that you need to have not just the fuel that you're dealing with, but also oxygen for it to react, and also some sort of energy source or ignition source to get it started. So when you're looking at the overall hazard, whether you're doing off-site consequence analysis or folding into a hazop study, you really need to think about, hey, I've got the potential for release, or I've got a fuel source. Is it able to find oxygen, and is it able to find an ignition source? Beyond that, even if it finds an ignition source, not everything translates into releasing the kind of energies that we just spoke about when we look at the enthalpy of combustion. When you're looking at a total quantity of this flammable substance, yeah, even for the worst case scenario, you want to look at it forming a cloud and then finding something to ignite. But only 10% of the material typically participates in the explosion from these worst case events and those kind of worst case assumptions. When you look at it on a more realistic basis, you see for a vapor cloud explosion, typically a 3% yield factor for the total amount of material released is usually more realistic, and things that are observed when releases have occurred in the past. And also, again, keep in mind that it's got to find the oxygen and ignition source, and not everything in the cloud will be in the flammable range. That's why not everything translates into releasing the total potential energy associated with that cloud. When you represent these overpressure impacts, just as if you're looking at a toxic release, usually overlay that on a map and identify an isopleth or a general area or boundary where past that boundary you don't have the kind of overpressure impacts or thermal radiation impacts that can impact buildings or injure individuals. So just like when you're looking at toxic releases, you'll overlay the results of your flammable release calculations and the off-site consequence analysis onto a map in that isopleth form. So let's talk about toxic gas releases and general modeling considerations and the kind of things that are associated with the phenomenology. When you're looking at airborne toxics, and that's usually what the concern is for the EPA and state ARP programs, because their jurisdiction is protecting the community. How can the community get impacted from toxics? Usually if it goes airborne, such that it can cross the site boundary and actually impact individuals. So the concerns, or the chemicals of concern, are usually ones that can volatilize, go airborne, and have a potential for acute health impacts. They're typically a vapor at ambient temperatures. If you're dealing with something that's typically a liquid at ambient temperatures, it's not likely to go very far. So you're looking at very low concentrations of vapor, and then for that low concentration of vapor, how does it disperse? So in many cases, the potential for hazard for things that aren't a vapor at ambient temperatures is very low. In some cases, and especially because of reactivity concerns and a history of people being concerned about things like cyanides, small releases of small particulate solids may also be of interest and may be encompassed by some state accidental release prevention programs. And again, you're looking at what you need to be concerned about are toxic concentrations beyond the fence line. This one slide illustrates some of the key things that you want to keep in mind. On the left-hand side, you see a vertical vessel that is having a vertical jet release. The material is volatilizing. It goes up in the air. Again, this is an airborne toxic that's being released as a vapor. Wind is going from right to left on your screen. And what can occur with a vertical jet release is initially as it goes up, it starts to spread horizontally as it starts dispersing in the air, and then it's transferring its momentum to the air, and the air is slowing it down. So the velocity starts decreasing as the cloud rises vertically, as it's still spreading out, and then of course the wind picks it up, and so it starts to move in the direction of the wind. So you're getting this momentum. You're getting the momentum transferred to the air, lost by the vapor. Then the wind is actually providing physical movement in the direction of the wind. Well, for a buoyant gas, it will typically continue to go up and spread both horizontally and vertically. For a heavy gas, either whether it be released under cold conditions or just have a high molecular weight, it can sink, slump as it's continuing to disperse. And in some cases, if the wind is very low speed, it can actually go upwind because as it's slumping and dispersing, it has the ability to go counter-current to the wind because of gravity effects. So all these things are things that you want to think about conceptually when you're choosing the right atmospheric dispersion model and when you're looking at releases of buoyant gases versus heavy gases and a realistic consideration of the hazard. I mentioned that whenever you have a release, it's going to spread in a three-dimensional aspect. If you look at it from a top view in terms of areas of a community that might be impacted, is it flipping on yours too?
Yeah.
Okay, must be something I built in the PowerPoint. My bad. So if you look at it top down, as if you're flying over the top of it, you're going to see it spreading out horizontally, but recognize that it's also diffusing and dispersing in the vertical direction too. When they do model these, because you don't know exactly what direction the wind's going to be blowing that day, usually what you do is you have a release point in the center of your screen in this case, and then an actual impact area if you know what the wind direction is. If you don't, they just draw a large circle based on that endpoint distance, and you do your emergency planning or do your worst case analysis based on that larger potential impact area. In your case, it's the blue circle on the screen. So key parameters for all atmospheric dispersion calculations, also for toxics, are temperature and wind speed. Higher wind speeds allow for faster movement and faster dispersion, building up lower concentrations as you go downwind. And then when you consider heavier than air releases, you have, is your screen keeping up? Okay, good.
Yeah.
When you're looking at heavier than air releases, you're looking at terrain effects, surface roughness effects, and understanding all these different phenomenology, especially for heavier than air releases and the models that you use, can be very important. Okay, so let's talk a little bit more about release phenomenology and then get into some specific examples. First thing you want to consider, as I hinted to before, is what is the phase of the material at ambient conditions? Whether it be flammable or toxic, is it something that wants to be a solid at ambient conditions and pretty much doesn't want to go anywhere in terms of getting off-site? Is it a liquid that can spread out, have maybe an environmental impact, but be less likely to go across site boundaries and impact people? Or is it something that wants to be a gas at ambient conditions? such that even if it is released as a liquid, it's going to rapidly volatilize, vaporize, and then want to go off-site. So these are the kind of things in this little sketch in the lower left. You know, if you reach a vessel, whether the vessel's at high temperatures, high pressures, a key consideration is what does the material want to do at ambient conditions once it is released. Also, understanding the hazard properties. Everybody's familiar with the fire diamond in the upper right-hand corner that deals with levels of toxicity, flammability, and reactivity, and gives general weightings to whether it's a 0 for a minimal impact or 4 for an extreme impact when you're looking at toxicity, flammability, and reactivity. Those are the kind of things that emergency responders have used for a long time to characterize those kind of hazards. Those are actually, not coincidentally, quite useful to the individual who's trying to understand the hazard, model it using off-site consequence analysis, because it's really the toxicity effects that you need to be concerned about. Things that have a higher toxicity rating are going to be of more of acute interest if it goes off-site. Things that have a higher flammability rating also, and things that are reactive can also get in trouble, and we'll talk about cyanides in a few minutes, can also get in trouble and cause other problems that can release toxic materials and have a potential off-site impact. So this fire diamond that's been with us for a long time is actually a good reflection and a good first cut at understanding the kind of things that can occur if you do have releases of toxic materials. Understanding the process conditions. If you get something that is mixed with a volatile material, if it's at high temperatures, if it's at high pressures, well, even if it wants to be a liquid at ambient conditions, if it's under very high temperatures and high pressures, it can still, if it's got a catastrophic release, go airborne as droplets and become extremely volatile. So these release mechanisms are actually leak size, leak location, what the process conditions are, can be extremely important when you look at the overall impact associated with the release. The types of things that you need to model are things like buoyant gases or evaporative pool releases, horizontal or vertical jets. Then that tells you how much material is released. Then you look at, because it is buoyant, use a Gaussian dispersion model, and then look at how far it goes as it spreads both horizontally and vertically. Even if it's released at an elevated location and it's a buoyant gas, again, it's going to diffuse in a vertical direction as well as horizontal, and you can get toxic effects downwind, even at ground level considerations where people are. And also recognize if you got an elevated release location of a buoyant gas, perhaps your neighbors are in multi-story houses, or you've got apartment buildings nearby that have many stories to them. And where your receptors are with respect to the release height is also an important consideration. For heavier gases that are denser than air at ambient conditions or under release conditions, for example, ammonia is a molecular weight of 17. Under release conditions, it's typically cold. So that even though it's a lower molecular weight than air, which is typically 29, that can tend to sink and become a heavy gas because it's very cold at the point of release. And so that's why ammonia gets a lot of attention when you're looking at toxic gas releases. So again, for heavy gases, yeah, you may have to model an evaporating pool if you've got a large release of material into a diked area, for example, or if you get a release in the vapor space, a horizontal or vertical jet. Other types of phenomenon that you may need to model that maybe aren't as quite as common are pressurized liquid releases, liquid spills of a pure substance, a spill of a solution, a vapor cloud fire or explosion, a BLEVE, a boiling liquid expanding vapor explosion, particulate releases, which we'll talk about in a few minutes, reactive chemicals. Is it going to react with the water in the air? Is it going to react with other chemicals that are nearby? All these things need to be considered with respect to the kind of release that you've got, and it may come into play with the types of models that are chosen. There's a variety of different models, from simple, give it a few parameters and you get an answer, to very complex models where you need to really understand a lot of the chemical properties and things that go into it. As the person who's doing the off-site consequence analysis, you need to understand what level of detail do you need in the results, what kind of phenomenon are really important during a release, and that helps that helps guide you in terms of the level of detail, the amount of effort that you put into the analysis, and of course what software you choose. So on the left-hand side of the screen, I've identified a lot of common software packages. The reason why there are many software packages for offsite consequence analysis, and this is just a snapshot, is for different situations. You may want different levels of detail. You may have to model different parameters or different types of toxic or flammable materials releases. So let's go and look at a couple of examples that kind of illustrate this consequence modeling and how you might apply it to different substances. First of all, let's look at ammonia. A very common substance. It's used in refrigeration, selective catalytic reduction, water chemistry, pH control, a lot of different uses for ammonia. It's been with us for a long time. It's got properties that are very well known. It's used in most communities. It's used throughout the world. And it's important to understand its potential hazard and how you manage and control those hazards. Well, let's start with the fire diamond. Basically, it's considered a minor flammable. Its lower explosive limits are somewhere between 16 and 25%, depending on what references you got and depending on what kind of conditions the release is. Health hazards, quite serious. It's something that is quite odoriferous. It's got a low odor threshold, which is very useful for helping you know that if there's a release occurring, but also if it gets up to a certain amount, it can have very acute health effects too. It's not very reactive when in its typical usages, and it doesn't have any special hazards. When you look at properties, it's got a low boiling point, which makes it a really useful refrigerant, but it also means that you need to consider that if there is a major release, it's often going to be at cold conditions, and if you get a large liquid spill on the ground, recognize that it has the potential to volatilize very easy as heat from the environment transfers into the ammonia spill. One of the things to really consider is application of water. I've talked to many emergency responders and a lot of folks at plant sites who are aware of the affinity for ammonia to water, and if there's an ammonia release, they'll want to knock it down with a fire water monitor or some sort of fogging type mechanism. All well and good, but if you start applying water directly into the ammonia spill, which to some people makes sense because, hey, well, let's dilute the ammonia and it's not going to have that impact. What you're really doing, or one of the things that you're doing, is you're taking water at ambient conditions, it's much warmer than the minus 28, hopefully, and you're putting that into the liquid ammonia that's been spilled. If you do that, you're rapidly adding heat into the ammonia, and what is it going to want to do? It's going to want to vaporize. So you got a real concern if you add large quantities of water to an ammonia vapor spill or an ammonia liquid spill, that it can volatilize rapidly, flash back on the emergency responder, and release a lot of ammonia very quickly. So understanding these properties is not only important from an analysis issue, from a design issue, from a protection issue. As an emergency responder, understanding these properties is critically important. Rapid dissolving in water, we discussed that. The molecular weight. If you release ammonia in its vapor form at ambient temperatures, it's actually going to want to be buoyant or rise. But much different response and release properties than if it's cold and it wants to sink and continue and keep large concentrations at ground level. So understanding these properties and also the release conditions is super important, not only for the analysis but also for the emergency responder. Dispersion characteristics, if you don't know any better, assuming it as a heavy gas and can build up concentrations at ground level is a good idea. If you've got a vessel full of ammonia at ambient conditions, or 68 degrees Fahrenheit, 20 degrees C, 8.5 atmospheres is the pressure that it's going to be built up to. So it's got a real potential, real high vapor pressure, and a real ability to volatilize and disperse. And of course, the high latent heat of vaporization means that it's an excellent refrigerant. It's inexpensive. It's a very effective refrigerant. And also, when it's released in the environment, It doesn't have any direct environmental impact at low concentrations, and so they use it for selective catalytic reduction and actually to reduce NOx emissions. So in a lot of cases, it's an ideal refrigerant, minimal impact on the environment, and very inexpensive to produce, and that's why you see so much usage. From an engineering perspective, it's terrific. From a human body perspective and reaction with people, not a good material. So let's talk a little bit more about that. This is just an idea of the saturation properties. If you look at 1 bar of pressure, 1 atmosphere of pressure, basically 14.7 psi absolute, you'll see that it crosses that at minus 28 degrees C, and that is that's basically your that's the point that we just talked about for the blending point. Recognize that as ammonia disperses in air and its vapor pressure lowers, it can go below that minus 28. So you want to be cognizant of that if you're an emergency responder. I've heard many cases where emergency response personnel have actually been in a vapor cloud with the proper protective equipment, of course, and they can tell that their protective clothing that's often polymeric, and because it wants to be impervious to ammonia vapors, it starts to become very non-ductile and very brittle as they're working the emergency. These are things that you want to keep in mind, again, understanding the properties of ammonia. When you're looking at release phenomenology, again, with like for all chemicals with blending points below ambient conditions, if you have a liquid spill and vapor comes off, it's going to actually take heat away from the liquid pool, and that liquid pool will stay there for a long time, but the amount of vapor that's coming off also decreases with time. You can use that to get a more realistic appreciation of the release rates and the amount of concentration it can build downwind. We talked about partial pressure of ammonia in the air. One of the things that keep in mind is when you're looking at an ammonia release, often it's reacting or helping condense water in the air. So you're actually looking at the water droplets rather than the ammonia. It gives you a visual indication of the ammonia release. And also, when you're releasing it in liquid phase, it's going to volatilize often as the pressure goes down. If you got a breach in a vessel and the vessel's at fairly high pressures, as the liquid comes out, it's going to want to volatilize, which means that it rapidly breaks into droplets in the air and forms an aerosol in many cases that hugs the ground and maintains high concentrations of ammonia at very low to the ground. Software that is good for modeling that, SLAB, Aloha, RMP Comp, very good for modeling episodic releases of anhydrous ammonia. This is the cross-section that we looked at earlier. This definitely applies when you're looking at anhydrous ammonia releases. Basically, you can get a vertical jet. We're actually still in the drawing. You can get a vertical release, and if it's cold, it can sink. It can even go upwind. So if you're an emergency responder, noting the wind direction is important. Also noting the temperatures. If the wind speed is low, you need to be very careful about where you position yourself and emergency response equipment to minimize potential exposure effects. So we've looked at anhydrous ammonia. Basically, ammonia is pure form. It's often used for selective catalytic reduction, pH chemistry, and certainly ammonia refrigeration. It's also used for farming in basically fertilizers that can be applied. In all those cases, you can use the pure form anhydrous ammonia. In some cases, selective catalytic reduction and pH control, you can use it in its form when it's mixed with water as aqueous ammonia. When you mix it with water, because of its affinity, it doesn't want to release as much. It doesn't want to volatilize as well. So it's inherently a lot safer material to use when you're using it for those applications where you can. Obviously, for refrigeration, except in very unusual types of systems, you really need to use anhydrous ammonia for common refrigeration applications. Okay, so general characteristics of aqueous ammonia. It's simply ammonia in a water solution, and it's often sold as 19.5% concentration. Not a coincidence the fact that the EPA threshold of interest is 20%. So a lot of people do it to get into the range of being an inherently safer substance and not having to deal with concentrations that kick it into the regulatory requirements associated with risk management programs. Now, something to consider, even though it's an aqueous ammonia, It behaves a lot different than anhydrous ammonia, but the toxicity issues, the vapors that come off, it's still ammonia. It's still NH3. It's still something that causes acute toxicity effects to people. So when you're looking at release phenomenology, it behaves quite a bit different than anhydrous ammonia. But when you're looking at the actual toxic effects of the concentration of ammonia in air, it's the same material. You're not dealing with a different chemical. All right, and I mentioned some of the key uses before. When you're looking at releases, the differences in release phenomenology are why a lot of people use aqueous ammonia. For pound per pound for the amount of ammonia you get, obviously you're paying a lot more if you're using it industrially because you're really buying a lot of water that comes with it. So again, it's behaving differently. The vapors that evolve from the liquid surface, if there's spill, they're a function of the concentration in water, the pool surface area, temperature and wind speed, and also time. But in all cases, the amount of ammonia that volatilizes off of an aqueous ammonia pool is going to be a lot less than an equivalent anhydrous ammonia release. And also, if you're releasing vapors off of like say, a blanket gas in a tank of aqueous ammonia, you're dealing with a fairly low vapor pressure and a much, much lower than anhydrous ammonia. So the amount of material volatilized is a lot less. The illustration that I presented there really illustrates that the kind of release phenomenology really involves a two-stage process. Unlike anhydrous ammonia, which can come right out of a tank and volatilize immediately, aqueous ammonia is going to pretty much have the ammonia sticking with the water. It's got that affinity, it wants to stay with the water. So when you look at a spill from a tank of aqueous ammonia, it goes into a diked area, usually you've got a dike around there, and that solution of ammonia basically stays within the dike area. It's not frothing, it's not rapidly volatilizing or boiling off, but you do have a vapor pressure of the ammonia that drives the amount of ammonia vapor that's coming off the top of the solution. That is what gets fed into your dispersion model, and then you look at the offsite impacts. Now, when the vapor comes off, typically you don't have the complexity of an anhydrous ammonia release where you need to worry about what's the temperature, is it a buoyant gas, or is it a heavy gas. Typically, as the vapors come off, you've already got a material that's pretty much at ambient conditions, so it would typically behave as a buoyant gas. For that reason, there's simple calculators and software that can easily model it as a buoyant gas. This chart just kind of illustrates the differences in vapor pressure associated with the concentration of ammonia in the solution and also the temperature. And you'll notice that it's not linear, and as temperature goes up quite a bit, you get quite a bit more vapor pressure. As the concentration goes up, it's not linear, and you get quite a bit more vapor pressure of ammonia that comes off. Various software packages like Aloha have this type of vapor pressure calculation built in there. Also, you can get various tables. What's important to you is to understand the overall phenomenon. When you get a solution release, you're looking at vapor pressure, and that gets fed into the dispersion model. When you're looking at regulatory concerns, what I want to share with you is the catch basin concept. Basically, a catch basin can minimize surface area. If you've got an aqueous ammonia tank, if there's a breach, if it goes in the diked area, what's really driving the potential offsite impact is the surface area of that solution spill. So if that solution is directed into a containment or a catch basin, something that's a little deeper and minimizes surface area, it allows a lot more time for emergency response and disposal of the liquid, and it minimizes the amount of vapors that come off the top of that spilled material. By doing that, you minimize offsite impact, and in a lot of cases, you can decrease the offsite impact to the point where you don't necessarily have to do the depth of regulatory programs that you would otherwise if you had a very large surface area that causes a greater offsite impact. Another key consideration for ammonia, and especially for anhydrous ammonia and a lot of other materials that have very high vapor pressures, is what about liquid-filled piping that can get blocked in? Often the anhydrous ammonia liquid is below ambient conditions. So if you block it in, and most refrigeration engineers understand this and try to avoid it, what I want to do is explain the concept is that if you've got cold liquids with high vapor pressure that are blocked in and isolated on both sides of, say, a piece of piping, what happens is it starts to warm up to ambient conditions. As it warms up to ambient conditions, it wants to expand, exert pressure on the sides of the pipe, and also it's got a higher vapor pressure. So when you're looking at that thermal coefficient of expansion, the increase in vapor pressure, it can provide, you can rapidly build up pressure inside that piping, which puts significant tensile stresses on the walls of the piping, and in many cases can lead to rupture. It depends, of course, on the temperatures that you started with, the temperatures that it builds up. Is the piping exposed to sunlight? Does it get really hot? And so all these things can go into how to deal with that. As a designer and as an operator of a facility that deals with anhydrous ammonia, what you want to do is make sure that you minimize the potential for blocking in liquid anhydrous ammonia such that the thermal expansion, the vapor pressures can build up to the point of rupture. And on the next page, I provided a little bit of an equation that illustrates how these things relate. The change in pressure is basically a function of the difference in the volumetric coefficient of expansion of the pipe versus the material in it. Usually the pipe's not going to be able to expand as fast as the material, as well as the vapor pressure buildup. It's directly a function of the temperature change for what it started versus what it ends up with if it's exposed to sunlight or if it just builds up to ambient conditions. And also you need to build in the compressibility factor. And what you get from that is what that pressure increase is in that pipe. And if that pressure increase exceeds the tensile strength of the piping itself, that's when you can get a rupture. So for ammonia piping and other materials, these are the kind of things you really want to avoid. And understanding the physical phenomenon and the chemistry behind it can be very important. So I've illustrated the differences between ammonia and anhydrous ammonia and also aqueous ammonia and their uses because it kind of illustrates the range of things that can go on with respect to process conditions and off-site consequence analysis. What I want to briefly mention is solids. There are solids like cadmium oxide, potassium cyanide, sodium cyanide that have an acute toxic health impact. And in a lot of cases for these accidental release programs, you need to be worried because of the small particle size that they can get off-site and disperse. Typical hazards are inhalation, ingestion, skin contact. There are ways to model them, less common applications, and you've got to be very careful. And you've also got to consider how do you get the material off-site. Well, one way to do that is to have a breach of the container or something that drops, and its impact on the ground provides you with a certain airborne release fraction that gives you a source term or a starting point for how much material can be picked up the wind and go off-site. So you need to look at several different types of phenomenon, the airborne release fraction, the wind speed, and what these small particles do as they can disperse off-site, and that gives you an appreciation of what the toxic concentrations can build up to. So these are the sort of things you may also need to model. Can be very different from gas releases, even though as the particle sizes get smaller and smaller, they're going to behave more and more like a gas in terms of their ability to travel distances. So you've got particles, you have to have some ability to get them airborne and have a source term. You've got a dropout rate due to gravity, and based on particle size, with very small particles, you might have actually some dispersion characteristics that conform more to a buoyant gas than a lot of other things. So a lot of things come into play, and you have to be very careful with this. And also keep in mind that the dispersion of the material may not even be the most important issue. Even though these state programs may pick up things like sodium cyanide as important issues that can travel off-site, the fact is that one of your major concerns is potential mixing it with acids, which can cause a reactivity hazard, where the acid mixes with the sodium cyanide, and you can generate hydrocyanic acid, which basically HCN is used in gas chambers, and at very low concentrations can have very acute health impacts. So keep in mind that in a lot of cases you have to evaluate hazards and dispersion based on what the regulations require, but in a lot of cases you need to go beyond that. Consider reactivity hazards, what else can be going on, and to consider that as part of your overall hazard assessment. So what I've tried to do is get into some of the details that go behind some common chemicals and what happens when they're released, and put that in the framework of understanding this offsite consequence analysis as part of the big picture in terms of understanding risk. It still falls back to understanding the severity associated with a certain event and the probability of that event to put things in perspective. So you can separate, as in this figure, the high-risk scenarios like scenario 5 that might have a high frequency and high consequences from low-risk scenarios like scenario 4 that also may be very frequent but have low consequences and shouldn't deserve nearly as much attention. So those are the key things that I wanted to impart. I also wanted to provide some additional information and references. Those are in the last 2 slides of your package. And also, I just wanted to kind of make sure that I provide an opportunity to ask questions, and also contact us if you have additional concerns, general interest areas. We spend a lot of time training folks as part of conferences. We do regional seminars where we go over the various issues and elements associated with risk management programs, CalARP, and process safety management programs. And so we really welcome an opportunity to interact with you and provide some guidance. And so you're welcome to call at any time. And of course, as consultants, we do a lot of work, not only in California, but throughout the United States and also internationally too. So yeah, I'll just kind of open it up for questions. And you can go ahead and use your chat feature or phone in, and we'll be happy to address that. We also have the option, as I mentioned earlier in the presentation, to dial you in so you can be heard or interact with some of the other participants associated with this webinar.
Steve, we do actually have a question. Another common chemical is chlorine. How do the consequence analysis techniques that you discussed relate to chlorine?
Okay, well, that's a good question. Chlorine has a low boiling point. It's acutely toxic, and for those reasons, more and more, a lot of the water treatment applications for chlorination and disinfection have been converting more and more to use of sodium hypochlorite, ozonization, and other types of disinfection procedures. But still, chlorine is an excellent disinfectant, and as a chemical, chlorine may be one of the if you look at our standard of living, ammonia and refrigeration has really enabled us to prolong food life, has made food more readily available and cheaper to help feed the hungry population of the world. In many respects, chlorine has a similar, very positive impact on our lifestyles and the ability to support the world's population by disinfecting water and making waterborne diseases much less common when you apply chlorine. Now, as we've evolved, we've also found ways to say, oh, gee, it'd be inherently safer if we mix it with water and have sodium hypochlorite that can go ahead and provide those disinfection capabilities. But still, it's very effective disinfectant, and when handled properly, it's also very safe. Chlorine also cannot be diluted or made inherently safer for many types of chemical processes. One of our clients is a aluminum smelting facility where they bubble chlorine through the aluminum to remove manganese contaminants. So chlorine still has a lot of good uses, but again, like I mentioned, the challenge is the fact that it's got a low boiling point and acute toxicity. And in a lot of respects, the kind of phenomenon that we talked about for anhydrous ammonia, whereby if you get a liquid spill, it can rapidly volatilize. You don't want to throw water on it, even though chlorine obviously has a good affinity for water. If you get a breach in the vapor space, if you get a breach in the liquid space of a vessel, you get a lot of liquid coming out that's going to rapidly get heat from the environment, volatilize, and release a lot of chlorine. A release in a vapor space can be a lot different. In fact, you might get an initial release of large amounts of chlorine vapor, again, high vapor pressure and high pressure in the chlorine cylinder. But what's going to happen is that release of vapor is going to remove heat from the liquid that's left in the vessel or cylinder, and that liquid that's left in there is going to be cooler. So what's going to happen as the liquid cools, vapor pressure goes down, So your release rate into the air goes down. And in fact, if you look at it over time, that release rate and chlorine, an amount of chlorine that's volatilizing going in the air continues to decrease. And a lot of people have used the term chlorine freezing, erroneously, in my opinion, but I've used that term to identify that phenomenon that as that liquid pool cools, it eventually reaches the point of equilibrium where the amount of heat coming in from the environment balances out the heat that's taken off by the vapors, from the vapors on the that are coming off the liquid, and you reach an equilibrium situation with low volatilization rates and very, very cold liquid that's left in the chlorine cylinder. But again, it's still chlorine, and as an emergency responder, you've got to be aware of that. You've got to understand the chemical properties, not only from a toxicity perspective, but what's physically happening, so that you realize that chlorine's still there. It's not in a safe configuration, and you want to avoid applying heat. You want to be aware that if it does find a way to get heat or volatilize, it can be extremely hazardous. So a lot of the techniques and modeling considerations that we use for anhydrous ammonia will also apply to chlorine. Chlorine also wants to react with water in the air. One of the other problems you've got too is if you have small chlorine releases over time, it can react with water in the air and make hydrogen chloride, which condenses on equipment and can be acutely corrosive. Okay, that's about it. Anything else?
That's it.
All right, well, thank you for joining us for our continuing series on process safety and risk management, and we'll look forward to your attendance next time. Thank you.